Hey everyone, and welcome back to this class, Advanced Convolutional Neural Networks. In this lecture, which I consider to be optional for this course, I'm going to show you the intuition behind another new and novel CNN architecture called Inception. Inception was invented by the guys over at Google and also won some of the ImageNet challenges. Like the ResNet, you can sort of break it down into the main principle and specific implementations. So in this lecture, we're going to talk about the main principle. And some of the famous implementations include Inception v3, Inception v4, and GooglyNet. In fact, there's even a network called Inception ResNet where they combine the ideas behind both Inception and ResNet. So what is the motivation behind Inception? Recall that choosing hyperparameters is hard. What should our filter size be? What size are the patterns in the image that we're trying to find? In fact, we may not even know these things when we're building our net, and perhaps such assumptions shouldn't be built into it. So the idea behind Inception is this. At every layer, instead of doing just one convolution with a particular filter size, we do multiple convolutions with multiple filter sizes. So for example, a 1x1 convolution, a 3x3 convolution, and a 5x5 convolution. By using same mode for all our convolutions, all the outputs end up being the same size, and we can therefore concatenate them all together along the feature maps dimension. So they just all end up being different features. In actuality, the picture is a little more complicated, but it follows the same idea. Basically, we just add more stuff. Stuff as in more convolutions, batch norms, and pooling. All the stuff you already know and are comfortable with. So in the actual Inception module, the 1x1 convolution branch stays the same. In the 3x3 branch, we actually do a 1x1 convolution first, and then 2 layers of 3x3s. In the 5x5 branch, we do a 1x1 convolution first, and then one 5x5 convolution. We also add an additional branch called the pooling branch, which does a 3x3 average pool, and then a 1x1 convolution. Note that every time I say convolution, I actually mean convolution and a batch norm, since batch norm has become pretty standard nowadays. There are quite a few variations on this with filters of different sizes, but this is just the first block of Inception v3. One question you might have at this point is, well, how can we concatenate everything together if we do an average pool? Does an average pool downsample the image? And in this case, it doesn't because we just use a stride of 1. So this sort of has a blurring functionality, just mixing in nearby pixels. At this point, the question you might be wondering is, why did we add these 1x1 convolutions in the first place? And the reason is actually very practical. Let's consider how many operations are required in the naive implementation of the Inception block, looking at just the 5x5 convolution. Now we're going to have to start putting some numbers on these, so let's assume our image is of size 32 by 32 by 192, which means it has 192 feature maps. Then the total number of multiplies we have to do, if our filter is of size 192 by 5 by 5 by 64, is about 315 million. But what happens if we insert a 1x1 convolution before the 5x5 convolution with 48 feature maps? Then the total number of multiplies we have to do is about 88 million. If we draw a picture of just the feature map dimensions, we can see that we go through a bottleneck. You first learned about this in the context of autoencoders, so you already know why this concept is useful. The idea is, by forcing the data to fit through a smaller space, we encourage the neural network to find a more efficient feature representation. This is a form of data compression. What's neat is, if you do a Google image search for GooglyNet, you'll see this network architecture that I often paste around in my courses when I'm trying to give you an example of a very large neural network. Well, this is in fact an instance of an Inception network. If you look closely, you can recognize all the little inception blocks in this network. What's also very curious about this image is that there seem to be these side branches sticking out of the intermediate layers. So another novel idea that comes from inception is that rather than just using the head of the neural network to make a prediction, we can actually use these side branches as well during training. To get some intuition on why that might be, remember that an image is shrunken down as it passes through the CNN. As this happens, each convolution is looking for features at a different scale. At the beginning, we might be looking for tiny features. In the middle, we might be looking for medium-sized features. At the end, we'll be looking for the largest features. So training like this ensures that, if perhaps there are different sized objects in the image, that we can capture them all by using different features at different scales. This is an important idea to keep in mind since, as you'll see, we'll be applying it again when we look at object detection. And this also gives you an idea of where the name Inception comes from. It's based on the movie, which contains a very similar idea. So remember that I consider this lecture to be totally optional. If you want to use Inception, it's no more difficult than using VGG or ResNet because all of them are included in Keras. If you want some implementation practice, a great exercise would be to take the approach we used for ResNet and first try to build an inception block. Once you get that working, try to build the first few layers of inception and keep adding to it until you get the whole thing.